Section: Introduction. In this section, we present details about PaliGemma's architecture and training. Many of our decisions are further explained in the following section. PaliGemma is a vision language model, VLM, that takes one or more images and a text description of the task as input. It then generates a prediction in the form of a text string as output. This simple input-output process covers various tasks like image classification, captioning, visual question answering, and dialogue. Additionally, by converting complex structured outputs into text, this model can handle tasks such as detection, instance segmentation, and more. PaliGemma consists of three main components: an image encoder, a decoder-only language model, and a linear layer for token projection. The image encoder we use is the shape-optimized VLM 400 meters model, which has shown excellent performance. The language model is the Gemma 2B version 1.0 pre-trained checkpoint, known for its balance between performance and size. We found that a simple linear projection works well for our model. The image and text inputs are tokenized and processed accordingly. The image is converted into tokens using the image encoder, while the text is tokenized with Gemma's sentence piece tokenizer. These tokens are then projected into the same dimensions for further processing. The input tokens for the decoder are structured in a specific sequence, including special tokens to mark the start and end of text. The image size is standardized for efficient processing. To maximize the model's capacity, we allow full attention on the entire input, including image and text tokens. This enables the model to consider all information when generating the output. The output sequence is auto-regressively masked to ensure accurate predictions. Our model focuses on natural language, object detection, and instance segmentation during pre-training, but it remains adaptable for other tasks after fine-tuning. Section Summary. In this section, we introduce PaliGemma, an open model that combines Vision language models with the Gemma family of language models. PaliX, PalmE, and Pali3 have shown improved performance on vision language tasks by scaling up models, with PaliGemma maintaining comparable performance using a sub-3B VLM. PaliGemma's architecture includes an image encoder and a decoder-only language model, enabling it to excel in various tasks like image classification, captioning, and visual question answering without the need for instruction tuning. Section: Pre-training. In this section, we will explain the pre-training process of PaliGemma, which consists of several stages. In Stage 0, we first pre-train the individual components of the model separately. For PaliGemma, we use existing pre-training models without any customizations. We use a smaller image model called VLM 400 meters instead of larger models like VLM. For language modeling, we choose the Gemma 2B model, which balances size and performance well. Even though larger models are better at tasks like mathematical reasoning, smaller models like Gemma 2B can perform just as well across various vision language tasks. Moving on to Stage 1, we combine the pre-trained unimodel models and train the entire model on a mix of vision language tasks. Unlike other models, our goal is to train a base model that can adapt well to a wide range of tasks, not just specific ones. We do not freeze the image encoder during this stage, contrary to common practice, to allow it to learn spatial and relational understanding from harder tasks like captioning. In Stage 2, we increase the resolution of the model to better understand smaller details in images. We train the model at higher resolutions like 448 × 448 and 896 × 896 pixels to improve tasks like object detection and reading small texts. This stage focuses on enhancing the model's ability to process higher resolution images by providing more detailed examples. Additionally, we extend the text sequence length to capture more information in the images. Section Summary. In this section, we describe the pre-training process for PaliGemma, which consists of 4 stages. In Stage 0, we conduct unimodel pre-training using existing components without custom pre-training. Stage 1 involves multimodal pre-training on a mix of tasks to train a base model that fine-tunes well across various tasks, departing from freezing the image encoder to learn more skills. In Stage 2, we increase the resolution of the model to parse higher resolution images, focusing on tasks like detection and segmentation that benefit from higher resolution. Section Stage 3 Transfer. In this section, we have completed stages 1 and 2, resulting in 3 PaliGemma checkpoints at resolutions of 224px, 448px, and 896px. These checkpoints are filled with a wide range of visual knowledge but are not very user-friendly or suitable for benchmarking. Their training has mainly focused on the amount of learning data rather than creating an easy-to-use interface. To make these base models more effective, we need to transfer them to specific tasks like COCO captions, remote sensing (VQA), video captioning, or infographic QA. This transfer can involve fine-tuning for a particular task, adapting to new inputs such as multiple images or bounding boxes in images, or even instruction tuning. To demonstrate the capabilities of these base models, we transfer them to various academic benchmarks using a simple transfer method with minimal hyperparameters. Additionally, we introduce a mix transfer checkpoint that can be applied to a selection of tasks simultaneously, along with detailed captioning and answering data. While this is not exactly instruction tuning, it moves in that direction. We also transfer PaliGemma to tasks that involve multiple images as input, such as NLVR2, which requires analyzing 2 images to answer a single question. For all transfers, we fine-tune all model parameters, adjusting hyperparameters like resolution, epochs, learning rate, label smoothing, dropout, weight decay, and whether to freeze the VIT model. These adjustments are crucial for optimizing performance across different tasks. We suggest exploring typical values for these hyperparameters, with bold values indicating initial attempts. The best settings for each task are provided in the appendix. We analyze the sensitivity to these transfer hyperparameters and the overall transferability of the model in subsequent sections, showing that good results can be achieved with the suggested initial values. During the pre-training stages, we aim to create a model that transfers well across tasks rather than one that can be used out of the box. By exposing the model to a variety of tasks during pre-training, we ensure it acquires a broad set of skills. At the transfer stage, the model simply needs to identify which skills are relevant to the task at hand and adapt accordingly. This process is quick and requires only a few examples. We do not use any transfer datasets during pre-training and eliminate near-duplicate images from the pre-training data to accurately assess PaliGemma's transfer capabilities. The pre-training tasks include simple captioning on various datasets, OCR concatenation of text from images, VQA generation, object detection, instance segmentation, and grounded captioning. These tasks cover a wide range of skills and languages, preparing the model for diverse transfer tasks. It is essential to remove near-duplicate images from the pre-training data to evaluate PaliGemma's ability to transfer effectively to new tasks. Section Summary. In this section, we transfer the base PaliGemma models, pre-equipped with visual knowledge, to specific tasks like COCO captions and video captioning by fine-tuning them with a unified transfer recipe. We explore various hyperparameters such as resolution, epochs, learning rate, and dropout to optimize performance. The pre-training tasks mix different objectives like captioning, OCR concatenation, VQA, object detection, and segmentation to ensure the model acquires a wide range of skills for effective transfer learning. Section: Other pre-training details. In this section, we discuss other details related to our pre-training process. Throughout pre-training, we use a continuous learning rate schedule that allows us to smoothly transition between different stages without decreasing the learning rate. The pre-training schedule follows a specific curve for all stages, and the transfer process helps in gradually reducing the learning rate. We suggest transferring the model using a simple setup that adjusts the full model using a cosine learning rate schedule with a brief linear warm-up and then decaying. The model was trained using open source code on Cloud TPU v5e, although some pre-training datasets are not publicly available. During training, we distribute data, model parameters, and optimizer state across all available devices using JAX with GSP-MD. This strategy, called Fully Sharded Data Parallel (FSDP) sharding, involves dividing the data and computations among devices efficiently. We achieved a model flops utilization of 55%, resulting in 5,189 tokens processed per second per device. The model parameters and optimizer state are stored in float32 to ensure stable training, but we confirmed that using bfloat16 for model parameters during inference works equally well. A single training run of the final PaliGemma model on TPU v5e256 takes less than 3 days for Stage 1 and 15 hours for each Stage 2. Stage 1 involves processing nearly 350 billion tokens, while both Stage 2 combined handle about 90 billion tokens. Transfers take varying times on TPU v3 to 32, ranging from 20 minutes to 10 hours depending on the task. To prevent the model from becoming too sensitive to different image processing details in various frameworks, we randomize image preprocessing steps such as resize method, JPEG encoding, and apply slight inception_crop. To test the versatility of PaliGemma across different tasks, we fine-tune the pre-trained models on over 30 academic benchmarks. Importantly, none of these tasks or datasets were part of the pre-training data, and their images were explicitly excluded from the pre-training data. The results of these transfers are presented in a table. We select hyperparameters for transfer by exploring a range of values starting from the recommended ones. We make these decisions based on the validation performance of the transfer task or using a small, minimal set if validation data is not available. Once we determine suitable hyperparameter values for a task, we retrain the model using all training and validation data and report the final test results. We also conduct various ablations to gain a deeper understanding of training and transferring very large models, VLMs. These ablations involve running experiments with different setups, such as shortening the Stage 1 pre-training duration by 10x and reporting transfer results on validation sets instead of withheld test sets. The multimodal pre-training duration in Stage 1, with 1 billion examples seen, is relatively long compared to some other models. We explore pre-training durations of varying lengths, including completely skipping Stage 1, and analyze the impact on different tasks. Shorter training durations generally lead to poorer performance, with skipping Stage 1 entirely resulting in the worst outcomes. A pre-training duration of 100 million examples seems to strike a good balance, being 10 times shorter while still maintaining performance across tasks. Section Summary. In this section, we utilize an infinite learning rate schedule for pre-training, ensuring a continuous RSQRT curve for all stages without decaying the learning rate between them. We recommend a simple setup for transferring the model using a cosine learning rate schedule with a short linear warm-up and decay. The model is trained on Cloud TPU v5e, utilizing a fully sharded data parallel sharding strategy with a measured model flops utilization of 55%. Section: Causal Masking and Learning Objective. In this section, we explored various aspects of our pre-training learning objective. We made changes to the auto-regressive masking design and investigated the impact of different strategies on our model's performance. We found that using a prefix LM strategy like PaliGemma's was more effective than other masking approaches. Additionally, we experimented with applying the next token prediction loss on different parts of the input data and observed how it affected the model's learning. We also introduced new tokens to enhance Gemma's capabilities for structured computer vision tasks. These new tokens required careful initialization of their embeddings, and we compared different initialization strategies to optimize the model's performance. Furthermore, we delved into the decision of whether to freeze certain parts of the model during pre-training. Inspired by previous successful approaches, we chose not to freeze any parts of the model and observed improvements in tasks requiring spatial understanding. Lastly, we examined the design of the connector used to map output embeddings to Gemma's inputs. We compared a linear connector to an MLP connector and found that, in our case, the linear connector was more preferable based on performance results. Section Summary. In this section, we explore the impact of causal masking and learning objectives in our pre-training process. We investigate the effectiveness of auto-regressive masking strategies, such as prefix LM, and the application of next token prediction loss on suffix tokens. Additionally, we introduce new tokens for structured computer vision tasks and discuss the advantages of not freezing any parts of the model during pre-training, showing improved performance in tasks requiring spatial understanding. Section: Image Encoder, with or without. In this section, we explore the use of image encoders in various vision language models, VLMs. Most VLMs typically employ an image encoder like CLIP, SIG-LIP, or VQGAN to convert images into soft tokens before feeding them into the language model, LM. However, only a few works, such as Fuyu and Eve, have attempted to simplify this setup by eliminating the image encoder and directly inputting raw image patches into a decoder-only LM. While Fuyu lacks training details, Eve provides some information on training and different setups but with mixed outcomes. By removing the SIG-LIP encoder in PaliGemma, we create a unified decoder-only model. We conduct our Stage 1 and transfers using this configuration. Despite significant changes in the architecture, we adjust the learning rate for Stage 1. Although this architecture still lags behind, the performance improvement with longer pre-training duration shows promise. Notably, PaliGemma's SIG-LIP encoder has been pre-trained on 40 billion image text pairs, while the Fuyu-style model encounters images for the first time during Stage 1 pre-training and only uses up to 1 billion images in our experiment. This analysis confirms that decoder-only VLMs could be a potential direction for simpler multimodal models, even though they currently face challenges in training efficiency due to the inability to reuse vision components. Regarding image resolution in VLMs, PaliGemma adopts a straightforward approach by pre-training Stage 1 at a low 224px resolution and then upscaling to higher resolutions, 448px and 896px, in Stage 2. This results in 3 separate checkpoints for different resolutions. We justify this approach and compare it to the windowing technique, which has gained popularity recently. When we increase the input image resolution, we generally observe either neutral or improved performance across tasks. However, it is unclear whether this improvement stems from the higher resolution providing more information or from the longer sequence length leading to increased model capacity. By downscaling images to 224px before resizing them to 448px, we find that the improved performance is influenced roughly equally by both factors. PaliGemma provides resolution-specific checkpoints for each resolution, which proves crucial for performance. Transferring checkpoints across resolutions leads to significantly worse results, highlighting the importance of separate resolution-specific checkpoints unless flexible resolution modeling techniques are employed. Another method to enhance input resolution is by windowing the models, where the image is divided into sections and processed separately before concatenating the results. While this approach may be useful when higher resolution checkpoints are unavailable, it generally yields lower performance compared to native resolution models. However, windowing could still be preferred for speed reasons, although the speedup observed is limited due to the large size of the Gemma model. Section Summary. In this section, we explore the impact of image resolution and the necessity of image encoders in vision language models, VLMs. We investigate the performance of decoder-only VLMs like Fuyu and Eve, which omit image encoders, and discuss the trade-offs in training efficiency and model complexity. Additionally, we analyze the effects of resolution on model performance, comparing the benefits of higher resolution images versus longer sequence lengths in VLM tasks. Section: Stage 2 Mixture Reweighting. In this section, we discuss the Stage 2 mixture reweighting process. We observed changes in the pre-training mixture between Stage 1 and Stage 2. Unlike previous versions, PaliGemma always uses the full set of tasks but adjusts their weighting, giving more importance to tasks related to higher resolutions like OCR, detection, and segmentation. As an experiment, we trained Stage 2 with the same mixture ratios as Stage 1. The results showed a significant drop in performance for only 3 tasks: DOCVQA, ChartQA, XM3600, while the rest remained consistent. This suggests that while adjusting the mixing ratio had some impact, precise ratios may not be crucial when training a base model for fine-tuning. However, they could be more critical for few-shot learning scenarios where mixing ratios significantly influence task frequencies. We also tested PaliGemma's transferability under various scenarios. We assessed its repeatability, sensitivity to hyperparameters, and the number of transfer examples required. The results showed that transferring from the pre-trained checkpoint is highly repeatable across different tasks. We found that using a simplified hyperparameter setup worked well for most tasks, except for a few that benefited from specific adjustments like increasing the number of epochs, enabling label smoothing, and dropout. Furthermore, we investigated the impact of the number of examples on fine-tuning PaliGemma for new tasks. Our findings indicated that even with a limited number of examples, e.g., 64, 256, 1024, 4096, PaliGemma could achieve promising results. By varying learning rates, epochs, and batch sizes, we determined that a smaller subset of examples could still yield satisfactory performance, with 4K examples reaching within 10% of full data scores and 256 examples achieving around 20%. Additionally, we made several noteworthy discoveries, such as the effectiveness of simple resizing for segmentation tasks, the introduction of Count Bench QA for improved counting assessments, and issues identified in previous widget caps evaluations. We also found that certain annotations in images could work as effectively as prompts and that certain interpolations and generalizations were unnecessary or surprisingly successful. Our MMVP results demonstrated PaliGemma's superior performance compared to other models, showcasing its potential in various applications.